There are a couple different ways to synthesize ethers, so to create an ether through a chemical reaction. In this video, we'll talk about the Williamson synthesis. The reaction scheme for Williamson synthesis. We start with an alcohol, so just an R group carbon chain on alcohol. We need to add a strong base, and often that strong base is sodium hydride. So hydrogen with a negative charge, that hydrogen has two non-bonding electrons. It has a negative charge, so it's ionically bonded with sodium, so sodium hydride. Remember, bases have electrons they are willing to give away to create a new bond. So that hydride, negatively charged hydrogen, that's a strong base. So we add a strong base and we add an alkyl halide. So I'll keep it general. Let's do R prime. So this can be a different carbon chain or the same as the alcohol, and it's bonded to a halogen. So here we have strong base. Here we have an alkyl halide. And an alcohol. The result is the R group and the oxygen from the original alcohol will then be bonded to the R group from the alkyl halide. So that's R prime here. Byproducts are sodium with whichever halide is bonded to the bonded in the alkyl halide, and we get hydrogen gas. This is a favorable reaction. We're releasing hydrogen gas as a product. And then if we just look at this molecule here, we have an oxygen bonded to two carbon chains. So this is our ether. And this is how we synthesize an ether. We'll of course look at a specific example and the mechanism for this as well. So let's say we start with, we'll just do methanol. We add the strong base. Note that sometimes in ionic compounds, the ions, so the positive charge on sodium, the negative charge on hydrogen, are shown. Sometimes they're not shown. Both are acceptable in chemistry, so when you're looking at a problem, you might see the charges, you might not. Just remember, anytime you see a sodium or anything in the first or second column on the periodic table, that's always going to have a positive charge. So that means whatever else is paired with it has a negative charge. I'll add the charges in here just so we can remember that we have positive sodium, negative hydrogen. That makes it a strong base. And then we'll do chloroethane. So CH3CH2Cl. This is also another reaction where it doesn't necessarily matter what's above the arrow, what's below the arrow. As long as you have these two components, or these three components really present in the reaction, then the reaction will carry through. So if we just predict the product here, our alcohol, the R group on the alcohol is a methyl. And when we write the product, we contain in the ether the R group from the alcohol and the oxygen. And that gets bonded to the R group from the alkyl halide without the halogen. So now we have our H3CO from the alcohol, and then the CH2CH3 from the alkyl halide. And this is our ether. Our byproducts are sodium chloride and hydrogen gas, dihydrogen. Okay, so that's the reagents and products that we would predict. Let's now go through the mechanism to really explain what's going on here. So if we have methanol, this is our alcohol. We have sodium hydride, which we said is a strong base. So we have a base here. In our other molecule, the alcohol, alcohols can act as an acid or a base. If there is a strong base present, like the hydride, this will act as the acid. So acids donate protons, bases create new bonds to the proton. So here we have our hydride will create a bond to the acidic proton on the alcohol, the one that's bonded to the oxygen, and the electrons from that bond between oxygen and hydrogen will be owned by that oxygen. So this is our first step here. We're only doing a proton transfer, so an acid-base reaction. We have an alkoxide, H3CO-, the oxygen gained 2 electrons from the bond to hydrogen. This charge is balanced by the sodium. And we've created H2, so that product there in this first step. Now we have a negatively charged oxygen in the presence of the alkyl halide. So I'm going to draw out this alkyl halide now. I'm going to emphasize these carbon bonds. Now you might remember from Organic Chemistry 1, when we have an alkyl halide, so in this case the ethyl or the chloroethane, that chlorine to carbon bond is a polar bond that pulls electron density away from this carbon. That makes it an electrophilic carbon. This is where a substitution reaction can take place. So this is what's going to happen here, where we have the nucleophile, so the oxygen with a negative charge, willing to give away electrons, and the chlorine, a good leaving group, willing to leave and take the electrons in that bond. So now we have a substitution reaction here. So the oxygen from what was the alcohol, then became the alkoxide, is now bonded to the carbon that was part of the alkyl halide. The carbon to chlorine bond breaks, so everything else stays the same. That carbon still has 2 hydrogens and the CH3 group. And then our byproduct now, we still have sodium, and we now have Cl- as a result of that carbon to chlorine bond breaking. So here we have our ether. This is the mechanism, or an example of the mechanism for the Williamson ether synthesis. If we just practice some naming here, our product, we have a methyl group and an ethyl group. In the ether, those are the two groups bonded to the oxygen. So the name of this is ethyl methyl ether. And then we have first a proton transfer reaction. And second, a substitution reaction. And we produce our ethyl methyl ether.